Hello, my name's Chris, and we just finished that CS170 review session, but I guess this is the equivalent of a webcast. And what I'm gonna do is I'm just gonna basically blaze through some of the problems, not all of the problems. Ray's gonna have another video where he goes through all the other problems, or maybe not, we'll see, hopefully he does. So we'll just go ahead and do a select subset. Well, let's go ahead and get started. I'm gonna blaze through all these questions. I'm not gonna give you time to think. Let's pretend like I did, and you can pause the video, and that would be good, but you don't have to do it. All right, so how many lines will this code print as a function of n? Write a recurrence and solve it. You can use asymptotics so that if you're maybe off by a little bit, then it's fine as long as you're asymptotically correct. All right, so we see over here indentation error. Everything should be encapsulated by the if statement. All right, that makes more sense because this if statement didn't look that good. But all right, so you thought about it, you're done. We had enough time to think about it. Let's go ahead and talk about the solution. Now, if we look at this while loop, we see k, and k keeps getting halved each time. So how many times does this while loop run? It's gonna run log base 2 of k times. And on every single time that it runs, you're gonna run n print statements. So basically that inner loop, you can just account it for log base 2 of k times n. And after that, it's going to also recurse. So since we have that, we have our constant term over here. I hope you can see the cursor. But that's going to be our term over there. And notice that we swapped out the k for n because over here we just set k is equal to n. So we have this n times log n factor here. And over here, we also reduced down the problem size by half because we called midterm of n divided by 2. So this doesn't fit Master's theorem exactly. The proof for this, we won't talk about it now, and it's not talked about on the slides, but you can look at the solution for this midterm, which is available online, and it's going to show you how to upper bound it and lower bound it by n log n, and that's why it's going to be n log n. This one is Ray's question, so I won't talk about it. Hopefully he'll talk about it in a video. So for this one, I guess this one's not that juicy. I'll just go ahead and talk about the solution. N to the log n is that in big O of 2 to the n. Well, you can basically rewrite n to the log n in terms of 2 to the power of log n. That thing, this right here is the same thing as n if it has a base of 2. And you can basically simplify this into an exponential with log of n squared inside the exponent. And since log of n grows slower than n, even log of n overall squared grows slower than n, so this is going to be true. It is indeed upper bounded by this exponential. As for over here, the second question asks you if f of n and g of n are functions for the positive integers, then the answer is false. Consider the function f of n is equal to, as defined here, it's going to be n cubed or some big value whenever n is odd. And then whenever n is even, it's just going to be n itself. So since it's going to be really big when it's odd and really small when it's even, if we have something in the middle, then you can imagine that neither one of these is asymptotically bigger than the other. Because, I mean, at any point in time, we can find some n such that f of n is going to be small over here. Just pick an even number. And you can also find some big value for n if you just pick an odd number. And this will defy your attempts to confine it with big O. All right, topological sort. Which of the following will give you a valid topological sort for a DAG? This one should say, which will give you a guaranteed valid topological. Basically, it's guaranteed to be valid. So you can't sometimes give a valid topological sort, but sometimes you don't give one. That's not OK. We're interested in only the one. There may be more than one. Well, I guess if you fast forward, you're going to find out that the answer is B. It's just one of them. But let me go ahead and give you a couple counterexamples for A and C. So let me delete this, and let's go ahead and start. So order the nodes by pre-number. All I have to do is have some sort of traversal so that if you do it and then sort it by pre-number, then it's going to result in an invalid topological sort. So how about this? Here's an example. This is your start. And you start from here, and you go ahead and run DFS. And let's just go ahead and say you break ties arbitrarily. So you go to A first. And then, so your pre-numbers are going to, if you sort it by pre-numbers, it's going to look like this. It's going to be like S, A, and then whatever this is, we'll call this C and D. C, and then D. And then after it finishes all the way down here, it's going to come back up here, and it's going to traverse down to B. This is not a valid topological sort. Why? Because B needs to be before D. B is an ancestor of D, so this is not okay. This is very not okay. So for A, it doesn't work on this graph, so it's not guaranteed. What about B? B is going to work. I can't give you a counterexample because it works. C, order the nodes by the in degree. Okay, let's give you another counterexample here. So if I just draw a bunch of nodes and connect them in like a long line like this, then let's go ahead and count up the in degree of each one. So this one has 0 coming in. This one has 1 edge, 1 edge, 1 edge. And let's go ahead and sort these. So there's only one valid topological sort, and that is to go from left to right in that order. But because of these ones, if I tie break poorly, let me go ahead and call these A, B, C, and D. If I tie break poorly, I could say A, and then, oh, well, there's 3 things with in degree of 1, so let's just go ahead and put C there, and then B, and then D. Then this is invalid. You need to specify how you're going to tie break, and it's really hard to tie break when you don't really know any other information besides the in degree. So we have D at the end. That's okay. We have A at the beginning, but B and C over here, this is not okay. So here's our sad face. He's very mad that it didn't work all the time. So this isn't going to work out. Can we think of a counterexample? We just did together. Nice. All right, so we have Kruskal's MST. The bullet edges were added by Kruskal's. So this is the result MST. Hopefully it is a valid MST. If you were to look at it, yeah, it's going to be the best MST we have. And the question asks, which edge must have been added last? Well, which edge was added first? You can already tell. Because the way Kruskal's works is it basically considers the edges in sorted order, so only the smallest edge is considered first. It's very greedy. It wants to add the smallest edge that it can that's going to contribute to the MST. So it's going to look at this one over here. That's the very first thing it considers. And it's going to say, is it going to connect 2 vertices of interest? And yeah, it does, because nothing was connected initially. So 1 was the first edge to be added. And then a bunch of stuff happens, and then all these bullet things appear. And then at the end, we have 8. 8 is our biggest cost for the, 8 is our biggest cost edge. So it must have been the case that it was considered last by Kruskal and added last. All right, MST versus shortest path tree. Oh, okay, this one's a little bit long. That's okay. We can diverge into Microsoft Paint and have a nice time. So we can find a connected, undirected, weighted edge graph G and a vertex V such that the minimum spanning tree and the shortest path tree rooted at V are disjoint, and assume that the graph has a unique minimum spanning tree. That'll be useful. So let me go ahead and delete all this stuff and start fresh. So imagine I have a bunch of vertices, and hopefully without loss of generality, let's just go ahead and pick this one as our starting vertex. Let me also draw a bunch of connections and stuff. So this one goes here like that. So your goal is to find, we'll draw 2 things, MST, and then also the shortest path tree. So the way that you find the MST is you can either use Kruskal's or prims, but for our purposes over here, it's easier to use prims. And why prims? Because if we have, let me just go ahead and give these some arbitrary weightings. And if we run prims from V, it's going to look at all the candidate edges that it can add into the MST, and it's going to choose the shortest one because it wants to find a minimum spanning tree where the cost is minimized. So that's how greedy prim is. We can expect what greedy prim is going to do. And let's go ahead and draw the MST so far. We got this V over here, the same one, and we got this 3 because 3 was the cheapest. Okay, so let's just go ahead and context switch here. Let's talk about the shortest path tree. And the shortest path tree, you can imagine you're just going to run like Dijkstra's from V, like that's the very first step, so that you can find the shortest path to any other node. And again, if we're going to run Dijkstra's, then we're going to consider on our fringe these 3 numbers. And which one wins? Well, the smallest one. So the shortest path tree starts out looking like this. But wait a minute, our MST so far and our shortest path tree, we don't have to consider anymore because, because they already share an edge right here. And this was just from the very first step of prims, and we know prims is going to find us an MST, and if the MST is unique, this must be the only MST. And our shortest path tree over here, well, they already share an edge. So it's kind of impossible. If you're trying to search for a counterexample, it's not going to work out because if you run prims and the shortest path tree algorithm from the same vertex, then you're going to have a conflict where they're not completely disjoint. And that's basically what we just said. All right, so, All right, so we are given a directed graph with a positive edge weights. It's got positive edge weights. We wish to find the shortest path from S to T, and among all shortest paths, we want the one in which the longest edge is as short as possible. How would you modify Dijkstra's algorithm to this end? Well, I guess, how does Dijkstra's even work? One aspect that we should notice is it's going to keep track. Okay, here's a funny graph again, just a whatever graph, and there's some stuff connecting. Don't really care. And the way that Dijkstra's works is it keeps this thing like over here that's rather like distance. So this is the node, and this is the distance. And here's A, here's B, here's C, here's D. So let's go ahead and say that this is 8, and this is 4, this is 3. Okay, and then so if we're running Dijkstra's from A, this is our point of interest, then it's going to consider its local areas, and then eventually it's going to find some shortest path to D, some shortest path to C. So it's going to go over here, and it'll note, oh, the shortest path to D was 3 for me. Well, let's also keep something on the side here. This is our augmentation to Dijkstra's. So it's going to be the node, and instead of the distance, we're going to also keep track of the max edge length. Max E, we'll just call it that. So then over here, we'll go ahead and say for D, well, the longest edge that we encountered was 3. And then this is going to come in handy later. So we run Dijkstra's, and let's just go and have this be, I don't know, like 9. And then 12, let's go ahead and do this. So this is going to work out. All right, so then after this, you consider going to B, because that's the next cheapest cost. So we have B over here. It's going to notice the distance is here. And then also over here on our side new addition, we also consider 4 to be the shortest path. And then eventually you're going to get to the point where you're considering C. And you're going to find that the shortest path from A to C is probably, how are we going to tie break arbitrarily, I guess? So let's just accidentally find, well, this isn't going to work out. Let's say this is 18. Okay, so then the shortest path from A to C, we're going to consider, have a different color. Hello? Oh, there you go. So this way. So this way is going to cost 12, and then we're going to find that first. So it's going to look like this. 12 so far, and for C, our biggest edge so far is going to be 8. Well, how do we know that it's going to be 8? Well, we know that for C, the longest edge is either this edge or something that B contains. So we can basically use the previous information. It's either going to be that, the max of that, versus our current edge, which is 8. And that's going to be 8, because we can do that in our head. And then you can also consider that eventually, here's a different color, we considered this path. And then we realized, oh, well, the shortest path from C, let's look at the, it's 12. Well, I also have 12 here. We got to modify Dijkstra's so that if it's the same length, it also checks the max edge length as well. So it's going to see this, and it's going to say, oh, so your alternate path that got you a shortest distance of 12, your longest edge was 8. Well, maybe I can do better. And it's going to consider some stuff, and it's going to say, oh, well, my thing's 9, so my thing's not better. So in this case, it doesn't replace the answer. But you can imagine that this side structure is very useful for deciding whether or not we want to replace our shortest path with the same length shortest path, but something that's potentially better. And that basically says what we're talking about. Except they called it long, we called it max E. All right, so more true false. Where's Ray when you want a sub? I need a break. That's okay. You guys don't get a break, so I don't get a break either. If you increase the weights of all edges in a graph by 4, then the MST will stay the same. It is going to stay the same. You can imagine that, imagine all the possible spanning trees that you can have for a graph. And how many edges does it have? Well, it should have exactly v minus 1 edges. And if all the weights of the edges increase by 4, then you basically just increased all the spanning trees weights by the same cost. So the relative ordering shouldn't change. And so that's going to be true. The second one, if you increase the weights of all edges in a graph by 4, then the shortest path tree will stay the same. This one's basically a variant of that discussion question where we tried to say if you add some constant to all the edges in the graph, does the shortest path from one node to another node stay the same? No, it doesn't. So definitely the shortest path tree, which is even a bigger concept, is not going to stay the same. Can we think of a counterexample? Yeah, but the same one from discussion works, so I guess we'll just go ahead and skip that. All right, so DFS of a DAG. In a depth-first search of a directed graph, the endpoints of edge A to B have these pre and post values. A, and then some stuff, and then B, and then some stuff. Can the graph be a DAG? Another way to look at this is, let's just go ahead and draw the graph that we know it must look like. And I'll only draw things that for sure must be there. So we know that we have an edge, A to B, in parentheses, it shows. So it must be like this. I don't really care about the weight. And then it has a pre and post value of these. So what that means is at time equals 39, you know, I'm going to write the pre number over here. We looked at B. And then at time equals 45, we came over here. We saw A for the first time. And this is by running some DFS. So this is interesting. It looks like B could potentially be the ancestor of A. And then we look over here at time 74, you finish looking at A. And remember that in DFS, you never finish your own traversal until you completely traverse all your children. And so it must have been the case that if we finish B at 112 here, we started B, and then we went to A, finished A, and then came back to B. So it must be the case that B is an ancestor of A. In other words, there must be some kind of funny path over here that you took during DFS. It might include a node or it might not, but let's just go and say it looks like that. It could also have been that there is some other stuff over here and you did some searching and then you also had a direct path like that. But basically, you know that there's either a direct path or an indirect path from B to A. So what does this mean? This means that since there's an edge from A to B and there's a path from B to A, we have a cycle. If we have a cycle, we can't have a DAG. I guess it says explain very briefly, and I didn't do that. So I'm losing time on this midterm. Okay, true or false? In a DAG, the number of distinct paths between two vertices is at most V squared. This one is going to be false. And let's just go ahead and go into Paint instead of reading that blob of text that's supposed to summarize what I'm about to do. So imagine we have some sort of some graph like this, and I'm drawing all the vertices. And they're all connected, but the deal is every single vertex is connected to every single vertex on its right. And so this one's going to be connected to this one, and lastly, this one's connected here, 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 and also straight to the end. So you can imagine that if we have S and T over here, this is a nice linearized, DAG, and we want to find out how many distinct paths there can be from S to T. Well, this node right here, we can choose to include it on the path or not. And what I mean by that is you could either have a path that looks like this, and you hop over here, and you go here, and you go here, or alternatively, you could actually just skip it altogether. You could take this edge over here. You could take this edge like this, and skip over here, skip over here. But because every single vertex is connected to all the vertices on the right, basically any vertex can hop to any vertex on the right. In other words, you can skip vertices. So I could have a path where I say this one is going to be on the path, this one's going to be on the path, this one isn't on the path. And yeah, I can do that. Looks like that. And then another deal, I just say, you know what, I don't want anything on the path. Then yeah, you can do that. You can skip straight over. There's an edge like that. So how many different paths are there? I can directly count all that by looking at the vertices, and just saying, are they going to be on the path or not? So every single vertex, you can either include it or not. So that's going to be 2 to the power of, how many vertices do we have? We have 3 in this case. So we got 2 to the 3 here. You can imagine that you can apply this for the n case where you have n vertices, then you can have 2 to the n minus 2 unique paths. And this is an exponential looking function. And I guess I won't really prove that that's bigger than v squared. But of course, this is going to be greater than or equal to n squared for large numbers. And that's not going to work out. I guess we can get rid of this thing if we're working with large numbers. So it's just strictly greater than. And this is our counterexample. OK, every DAG has at least one source. This one, I guess we don't have to draw too much. We can just say, well, any DAG is a directed acyclic graph. You can have a topological sort for it. And if you have a topological sort, then the very first element, it must be the case that all the ancestors came before and there are no ancestors. So you know that that very first element in a topological sort has no ancestors, so that one's the source. And it's true, and some other reasoning that's probably similar to what I have. Every DAG has exactly one topological ordering. Is this true or false? Well, let me go ahead and give you an example where you can have multiple topological orderings. So we're just going to have a simple one over here. Oops. So we have over here S, and then we go over here. Here's A, and here's B, and here is t. What are the valid topological orderings? You can have S, A, B, T, or you can have S, B, A, T. So that's that. Some DFS stuff. Ray's going to talk about this. So he's going to explain what all the stuff about tree edge and back edge and stuff is and how to find the pre and post numbers. Find the SCCs. Oh, that's also Raymond. Oh, FFT, that's also Raymond. And algorithm design, divide and conquer. Okay, this one's me. So imagine that we have an array. Oh, I hope I'm not getting sloppy at talking because it's, what, 10:14? Maybe we should just conclude. Well, no, that's okay. That's okay. Well, I'll finish this one, and then we'll call it a day so that I can respond to my mom's iMessage. We are given an array A where n is greater than 1, so it's some sizable array, and all array elements are non-negative integers. Our goal is to find the maximum value of A of I plus A of j squared, where the indices I and j range over all the values such that you basically have I before j. And they can't be the same index, and they both have to be real indices. They can't just fly off the end of the array. That's not okay. Okay, so here is an observation. First of all, if it's a really small array, like just two things, I don't know, like 0 and then 8 or something like that, if here's your array, that's really easy. You only have one possibility. So that can be your base case. If the size is 2 or smaller, then just go ahead and compute it. And you know that the best possible case is the worst possible case. There's only one possible way to do this. This is I and this is j. But imagine that we have some big array. And how are we going to do this? We can just split it right down the middle and say it must be the case that the answer is one of 4 cases. Either I and j are here, and so that the best answer basically has I and j coming from the left half, or you have I and j over here coming from the right half, or you have I here and j here, or lastly, you have j here and I here. But one of these is funny, all right? Funny meaning it's not allowed. We know that I must be less than j, so it can't be this case. This is not okay. Not okay. But actually, this should be a happy face because then we have less cases to consider. So we have I and j over here, or I and j over here, or I and j are separate. So in this case, how can we use divide and conquer to handle it? Well, overall, this entire thing, it must be that I and j is somewhere from here. So what we can do is we can have this part be recursed upon and this part be recursed upon, and that's going to handle these parts respectively. And for this one, I manually handle it. So in other words, what I'm going to do is I'm going to find the maximum number from here and then find that. So that was the max 1. And this one over here, for j, we find the maximum possible j that we can. And we find the max over here, call it max 2. And then here is one of our candidate answers. And we can compute that. We can just go ahead and say whatever it is, if it's a plus b squared, then go ahead and compute that. Where b's over here, a's over here. And then we also have the recursive thing over here. So this one is result 1 from recursion. This one is result 2. And you basically have the option of taking this one if it's big, or this one if it's bigger, or this one if it's bigger. And that's essentially the solution for this. What is the runtime of this? Well, over here, I guess we had to compute the max over here. That was already linear time. We spent linear time already, and these recursive calls are basically 2 things of size half. So we can draw a recurrence relation for this. I say draw because I'm not writing. I have this funny stylus over here. So we have t of n is equal to t of, there's going to be 2 of them, of n over 2, and then plus some linear thing where we had to find the max. So what does this turn out to be? This is going to be n log n. How did you do that? Either you kind of recognize this from something similar. What is this? Oh, wait, merge sort, some similar. Or you could just apply Master's theorem, and you'll get n log n. But you can actually go faster. You can go faster than that if you go iteratively. Apparently, you can go divide and conquer faster, but I don't really know how to do that. But there is a way to do it iteratively in n time, so just linear time. What can we do here? All right, so let me go ahead and wipe all this. And I like blue, so let's go ahead and keep it. And imagine you have some sort of array here. And you know what? I'm going to tell you that there must be a maximum value somewhere in this array. And you know what? Just suppose that someone told us that it's right here, and it's the biggest number, 5. So all the other numbers are like, what, like 4, 3, whatever, smaller. But none of them are, either they are 5 or not. What does this say? Non-negative integers. Yeah, so it might not necessarily be unique. But if 5 is the biggest number, then it must be the case that you use it as I or you use it as J. So you use this as J, and here's I like somewhere over here. You pick one. Probably the biggest one would be nice. Or you can have I here, and you pick some J from over here. Why is this the case? Well, suppose that both I and J are not in this maximum. So like maybe I and J are like over here. Or yeah, if this was the case, then you'd get a bigger number if you swapped out this maximum with I. Either the same number or bigger. But nobody can do better without using the maximum number. And then what if I have like some I, J like this? Well, in this case, you know, you could swap out either one of them. You could upgrade J, and whatever J was, you could upgrade it to be 5 over here. So you can use the maximum element. It must be that the maximum element is either going to be I or it's J. And anything else, it can upgrade. So in this case, you can just swap out J for 5, and it's going to upgrade. So another way to look at this is if we just know the maximum element, then we know it's either going to be I or J. So we can find the max. Let me go ahead and make a list of all the things we need to do. We need to find the max, and this is linear time. And then after we have the max, consider the best answer where you say you're using the max as J. Then you basically use max as J. This is also going to be linear time. And in this step, you find the best possible I that you can. And the biggest one should be the best I. And then the third step over here is use max, sorry for the sloppy handwriting, as I. And this is going to be O of n as well. So basically, you have 2 candidate answers, and you should just take the maximum. If they're the same, then you can just pick whichever one you want. It doesn't matter. This will work out. So this is an iterative way to solve this. And this is Raymond's stuff. And that's Raymond. I'm not sure if he actually wants to talk about this one. And questions? Anyone have any questions? Oh, no questions. All right. You know what? Let's call it a day then. So good luck on your midterm Tuesday.